Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on linear control systems theory. Today we are going to discuss state estimation and dynamic feedback control for linear time invariant systems. State estimation is basically, as the name suggests, it is the estimation of the state vector, and when we do not have the full measurement of the state vector using the sensors, we try to estimate the state vectors, and we will see in this lecture how we do that. And the dynamic feedback control is the feedback control law that basically uses the state estimate instead of the state vector for implementing the feedback control, and we shall see how that works or how that is designed in this lecture as well. So last time we discussed the state space state feedback control using the pole placement method, and the summary of that is that suppose you have a linear time invariant system x dot equal ax plus bu, and suppose that this system is controllable, then you can design a control law of the form u is equal to minus kx. This is a linear control law, this is a linear gain, and times the this state vector. So then the dynamics of the closed loop system is given by x dot equal a minus bk times x. So if you want to make the dynamics of the closed loop system asymptotically stable, you have to place the eigenvalues of this a minus bk matrix into the open left half plane, and you can do that by proper choice of this k matrix if the system is controllable. So the closed loop characteristic equation is determinant of lambda I minus a minus bk equals 0. And now suppose we wish to place the poles at some locations of our choice, lambda 1, lambda 2 up to so on lambda n. Obviously for asymptotic stability we will choose these values in the open left half plane, and the complex poles will always be in the complex conjugate pairs if you want the k matrix to be a real matrix. Okay, so comparing the equations 1 and 2, you can determine the k. We looked at it last time, and we also looked at some examples. But the problem with this approach is that we need to measure all the state variables in order to implement this control law in practice, in practical projects. So usually what happens is that this x is a state vector which includes the internal variables in the system, and some of those variables might not be very easy to measure, and maybe your project is a low budget project and you cannot afford many sensors, and maybe the sensors are not so precise, their readings are not very reliable. Then in that case what will you do? So this lecture will address that issue. So the motivation for today's lecture is that full state feedback may be expensive, and we need more sensors to measure every state variable, so this increases the cost of the project. For some variables, corresponding sensors may not be available. That's another problem, and there may be noise in the sensors, and the state observers. Basically now this is the coming to the solution that state observer is something, an entity that can estimate full state vector using the values of a subset of state variables. So this is something we will discuss in this lecture, that we will not measure the full state variables, all of the state variables. We will just measure a subset of state variables, and then we will design a state observer which will use those measurements and calculate the remaining state variables from the subset of state variables. Just need enough sensors to make the system observable. Now we will also look at what is observability. In this lecture we will look at this property. This is very similar to the controllability in a sense that in order to design the controller, the system should be controllable, must be controllable. Similarly, in order to design the observer, the system must be observable. Then we shall see how we can determine observability, what is the definition of observability, and how the state observer is designed and how it is implemented. So output of a system, basically output of a system is anything that we wish to control in a system, any variable of the system that we wish to control the behavior of, and we usually measure the output. In feedback control, we measure the output using the sensors, and usually this output is a subset of or a linear combination of state variables. So where y is a measurement vector of size p cross 1, so you can have p sensors in the system, and then c is the measurement matrix of p cross n. So number of rows in c is equal to number of sensors, and number of columns in c is equal to number of states in the system. Then x is the state vector of size n cross 1. So this is the basically how the output of the system. This is the conceptual representation of the output of the system. So in general, for n state variables, you may be measuring having p sensors. Each of the p sensors may be measuring a linear combination of the state variables. Linear combination also includes a single state variable. So one sensor could be measuring a single state variable, another sensor could be measuring sum of two state variables, another sensor could be measuring difference between the two state variables, and so on. Observability. Now we come to the point. What is observability of a system? The ability to determine the initial value of the state vector from the value of the output that is coming from the sensors and the value of the input that is calculated using the control law or any other equation using the dynamics of the system. So we have three things. We have the output of the system, we have the input that is applied to the system, and we have the dynamics of the system, which is like x dot equal ax plus bu. So the equation of x dot is the dynamics of the system. The natural dynamics is basically represented within the system matrix, which is the A matrix, and the dynamics that are dependent upon the control input are represented by the B matrix. So using the dynamics of the system, the control input and the output, if you can use these three informations and determine the initial condition of the state vector, then the system is observable. And if you cannot calculate the initial condition of the state vector using these initial conditions, information, then the system is not observable. So why are we interested in the initial condition? This is because the dynamics of the systems are represented by an ordinary differential equation. So if you know the initial value of the state vector and if you know the dynamics of the system, then you can calculate the value of x of t by just solving the differential equation. Remember that differential equations are solved using the boundary values. So if you know the boundary value or initial condition, you can solve the differential equation. You can get the exact solution of the differential equation. Okay, now determination of observability. Obviously, this definition of observability for a linear time invariant systems is okay to understand the concept of observability. The concept of observability is that you are using lesser number of sensors, and with the lesser number of sensors you are able to determine the initial value of the state vector, or in turn implicitly you are able to determine the full state vector at any time t using a measurement of a subset of state vectors. But this concept does not help us in measuring the observability, in determination which system is observable and which system is not observable. So for determination of observability, a system is observable if and only if the matrices A, C of dimension n cross, so A matrix will be dimension n cross n and C matrix will be of dimension p cross n, as we discussed a couple of slides ago, form a matrix of size n into p, and this matrix is called O matrix or observability matrix, and it is represented by C, CA, CA square, and up to so on C into A to the power n minus 1. So if this matrix has rank n, then the system is observable. So the calculation of observability is very similar to the calculation of controllability, which is basically down to finding the rank of a particular matrix. In controllability, we have Q matrix, which is B, A square B up to so on, A into A to the power n minus 1B. And in observability, we have observability matrix, which is C A square up to so on, C into A raised to the power n minus 1. And if C is 1 cross n, which means that if you have only one sensor in the system, then O is an n cross n matrix, and the rank of O is n if and only if the determinant of O is not equal to 0. So really, for a single output system, for a system with a single sensor, the determination of observability boils down to only the determination of the determinant of a matrix. So you only have to calculate the determinant of O, and if it is non-zero, the system is observable, and if it is 0, the system is unobservable. Now we look at some example. So for example, this is a third order system with single input and single output. So basically in this output we are measuring x1 plus x2. So these coefficients tell us 1 times x1, because this is the first place coefficient in the C matrix. So this multiplies with x1, this multiplies with x2, and this multiplies with the x3. So in this system we have one sensor, and that sensor is measuring the sum of x1 and x2. So using the sum of x1 and x2, is it possible to determine all three states x1, x2 and x3 or not? This is a very practical information and very useful for practical purposes, that you need to find out whether it is possible to determine all three state variables using the measurement of only x1 plus x2. So we do this by just computing the observability matrix. In this case, the n is equal to 3. So observability matrix is CA square, because n minus 1 is just 2. So this is C. This is the second row is C times A, and the third row is C times A square. And then the determinant of O, if you calculate, it will become minus 80, which is non-zero. So the system is observable. So this is how you can easily determine the observability of a system, which is a very, very practical property, and you calculate it using simple mathematics. Okay, now we come to the next topic, which is linear observer or the state estimator. There are many state estimators, but in this lecture we will be discussing Leuenberger observer, which is a very common state estimator for linear time invariant systems, for which there is no disturbance and noise or uncertainties involved in the system. So suppose we have a system x dot equal ax plus bu, and we are measuring y is equal to cx, and and also you have to assume that this system is observable. So if this system is observable, then only then you can design the Leuenberger observer. And once you how do you design the observer? First, you choose the observer dynamics. The observer dynamics are basically two things. First thing is the copy. This is the exact copy of the system dynamics. System dynamics ax plus bu, the exact copy, same A matrix, same B matrix, same U, but here instead of x we have x hat. So this is the copy of the system dynamics. And then there is a correction term. This is a correction term. What is a correction term? Correction term basically is a gain, a constant gain multiplied by difference between the actual measurement from the sensors and the estimated measurements from the sensors using the state estimate provided by the observer. So if the observer is providing you the estimate of the state x hat, you calculate the so you predict or estimate the value of the sensors using the state estimate, and then you compare it with the actual value of the sensors. If these two values are equal, then that means basically x is equal to x hat, which means that no correction is required. So this difference will be 0, and whatever the value of L is, the observer dynamics will be exact copy of the state dynamics, and there is no correction term. Correction term will become 0 if x is equal to x hat. So this is the observer dynamics, and if the x is not equal to x hat, this correction term, this L gain, will be selected so that it will make corrections in the x hat dynamics, so that the value of the x hat will converge to the exact value of x. So we shall see how this happens. Once we define the observer dynamics in this way, next we go on to the error dynamics. Error is the difference between x and x hat. The dynamics of the error will be so x tilde is the error. X tilde is equal to x minus x hat, and the derivative of x tilde will be derivative of x minus derivative of x hat. And if you substitute x dot equal ax plus bu here, minus x hat dot equal ax hat plus bu plus L into c minus c x hat, then after some simplifications you get this equation, a minus lc into x tilde. Now this is the dynamics of the error, and what we wish is, we wish the error to go to 0. If we want the error to go to 0, the dynamics of the error must be asymptotically stable. If we wish the error to go to 0, the dynamics of the error should be asymptotically stable. So the design of the observer is basically determination of this gain value L, such that this A minus LC matrix must have all the eigenvalues in the open left half plane. Again, the design of the observer is basically determination of this gain value L, such that the error dynamics are asymptotically stable, which means that error goes to 0, or which also means that x hat goes to x as t goes to infinity. So we can only place the eigenvalues of A minus LC arbitrarily using L if AC is observable. So first we have to check the observability of the system. Only if the system is observable, only then the observer can be designed. If the system is not observable, the observer cannot be designed. Now we look at an example. So let's look at this second order system, where we have a single input and single output, and we are measuring state x1. So we have one sensor which is measuring x1. So first we check observability. This observability matrix is C, C, A. This first row is C, second row is C times A, and the determinant is 1, which is not 0. So the system is observable. So we can design observer for this system. Now what shall be the size of matrix L for the observer gain? So size of matrix L is always equal to the size of the transpose of C. So here C is 1 cross 2. So L will be 2 cross 1. So if the size of L is equal to the size of transpose of C, if C is P cross N, then L will be N cross P. This will ensure that L times C is N cross N. So once we have so this is the this will be the L matrix in our example, which is of the same size as the size of the transpose of C matrix. So now the eigenvalues of A minus LC are computed using the equation determinant of lambda I minus A minus LC equals 0. And if we plug in this equation, the eigenvalues are computed like this. So this is lambda I, this is A, this is L, this is C. So once we do these computations, we have the characteristic equation for the error dynamics: lambda square plus L1 times lambda plus L2 equal 0. So now let us suppose we wish to place the poles of the error dynamics at -1 plus -2j, which is in the left half plane. So the desirable characteristic equation will be lambda plus 1 plus 2j, lambda plus 1 minus 2j. So these will be multiplied. This is the factored form of the polynomial corresponding to these roots. And when we multiply everything out, this is lambda square plus 2 lambda plus 5 equals 0. So this is the desirable characteristic equation for error dynamics, and this is the actual characteristic equation for error dynamics. So if we compare these two equations, we see that L1 is equal to 2 and L2 is equal to 5. So once we select L1 equal to 2, L2 equal to 5, then the closed loop, then the error dynamics will have eigenvalues at -1 plus -2j, which means that error will go to 0 as time goes to infinity. Hence the desirable observer gain is 2, 5, and then the resulting observer would be x hat dot equal a times x hat plus b u and plus L into C multiplied by x minus x hat. So this will be the observer. This can be implemented in the microcontroller where you implement your controller, and this would just be a programming code in the system. So as far as your project is concerned, there is no additional cost, because in order to implement the controller you already have to have the computational capability in your project. So you can use the same computational capability to implement the observer that you are using to implement the controller. And the advantage is that instead of having full state feedback, you're just measuring, in this case we are just measuring state x1 and we don't have to measure the state x2. And next we look at how we first we look at another example, and then we shall look at how we can design the controller based on the state estimates. So this is the third order example where we have three states x1, x2, x3, and we are only measuring the state x3. So we are only measuring state x3, and we are trying to figure out whether we can determine the value of x1, x2, x3, all three states using only the value of x3. So we check the observability matrix. In this case is C, CA, CA square, and when we calculate the determinant it becomes -1, which is non-zero. So that means the system is observable, and so the observer gain in this case would be of the same size as the transpose of C. C is 1 cross 3, so L will be 3 cross 1, and it will have three elements, L1, L2, L3. Now we have to determine the values of L1, L2, L3 such that A minus LC has the eigenvalues in the desirable location. So this is the characteristic equation for error dynamics computed by determinant of lambda I minus A minus LC equals 0. So which becomes lambda cube plus L3 lambda square plus L2 lambda plus L1 equals 0. This is done in the same way as we did in the previous example. And now suppose we wish to place the poles at -3, -2 and -1, then the desirable characteristic equation will be something like this, and when we simplify it, it becomes lambda cube plus 6 lambda square plus 11 lambda plus 6. And when we compare this desirable characteristic equation with the actual characteristic equation, we get the values of the observer gains. So L1 here, L3 has to be 6, L2 has to be 11, and L1 has to be 6. So the observer will be 6, 11, 6. So this will be the observer gain, and now the observer design is complete. Next we look at the observer based controller design. So first of all, let us look at the big picture. If you do not use the observer, then your output y has to be exactly equal to x, which means that you have to measure all the state variables, and then you feed those state variables back into the controller along with the desirable value of the state vector, and then you can use the controller u is equal to x, u is equal to k times x desired minus x. Remember that if x desired is equal to 0, then this is simply u is equal to minus kx, which we saw in the previous lecture and in today's lecture's first or second slide as well. But if x desired is some constant value, you can just make the controller equal u is equal to k times x desired minus x. Okay, so this is the full state feedback controller, and its drawback is that we have to measure all the state vectors, all the state variables, and design this controller. But then there is this alternate method where you have an additional component, observer, in the system, which uses the information about u and y and the copy of the dynamics of the systems. So here the measurement is not the full state vector, it is some linear combination of the state vector. So we are using the value of the output and the input to generate the value of x hat, and then this x hat is fed back into the controller, and the controller is using x hat instead of this x. So this is the difference between this is the dynamic feedback compensator because of this observer dynamics involved, and this is the full state feedback controller. Okay, so the observer based dynamic compensator uses the estimate of the measurement is the subset of state variables x, and we design the control law using the state estimates, and the state estimates converge to the actual value of the state with proper design of the observer if the system is observable. So the system has to be observable and controllable for this implementation, and the system only has to be controllable with this implementation. Okay, the example is that for example, this is the same system that we just used in the couple of slides ago for observer design, and we have already designed the observer for this system, which was the observer gains we calculated were 6, 11, 6, and now we are trying to design use this observer, and based on this observer we are trying to design the controller for the system. So for designing the controller, first of all we have to check the controllability of the system. We formulate the controllability matrix Q is equal to B A B A square B, and then we check the determinant. Because this is a identity matrix has a determinant equal to 1, which is non-zero, so the system is controllable. And now we can place the closed loop eigenvalues at anywhere we want. Let us suppose we want to place the eigenvalues at -1. One of the eigenvalues we want to place at -1, and two of the eigenvalues we want to place at -2 plus -j. Again, I emphasize that complex eigenvalues should always be in complex conjugate pairs. So we can place these eigenvalues using MATLAB, and we can also repeat the calculations that we did earlier for controller design in the previous lecture. So in this case I use the place command in MATLAB. You can go to MATLAB, and in the command window you can type in help space place, and it will show you how to use this command. Basically you give the MATLAB give this function uses the value of A and B matrices and the desirable pole locations, and it gives you the value of the gain that will make the closed loop eigenvalues at your desirable locations. So the resulting closed loop system as well as the observer dynamics are given as follows. This was our the original system was x dot equal ax plus bu, and instead of u we have minus k. This is the k gain that we have calculated with our desirable closed loop eigenvalues, and then this is minus k times x hat. So in this case we are just trying to stabilize. X desired is equal to 0, so u is equal to minus k x hat, and this is the k and this is x hat, and this is what will be implemented in the controller. The dynamics are automatic in the plant. In the controller you should be only implementing u is equal to minus kx hat, and you will only be calculating the value of u which is equal to minus kx hat. And then this is the observer dynamics, which will be implemented fully in the microcontroller in the form of a difference equation, where you update the value of x hat at every time point using this equation, or a discrete counterpart of this equation. You can convert a continuous time equation into discrete time difference equation using MATLAB, or you can also use first order Hold filter or zero order Hold filter. This type of things are taught in a separate course which is called Digital Control Systems, and here we just give you this knowledge because you should know how what challenges are still there that you have to deal with in practical situations. Okay, so x hat dot equal a x hat minus b k x hat. This is the exact copy of the system dynamics above, and this is the observer gain. Observer gain is L, and this is Cx. Y is equal to Cx, which is the sensor value, the actual value from the sensors, and this is Cx hat, which is the sensor values, estimated sensor values using this state estimate provided by the observer. So this gain will try to correct the estimate until these two become equal to each other and the error becomes zero, after which this observer dynamics will be simply the exact copy of the system dynamics. And that's the end of the lecture. And so we have let me just revise today's lecture in a couple of minutes so that you know what we discussed in today's lecture. We started today's lecture with the recap of pole placement based controller design, and it will be on your screens in a minute. Here it is. So we started the lecture with the recap of how you design the controller using pole placement method, and this method is applicable for single input and full state feedback systems. So you have only one input variable or only one actuator in the system, whereas your number of sensors is equal to number of state variables. But then we went on to discuss some new concepts where you can basically measure only a subset of state variables and then design the controller using that. The main purpose is that to use lesser number of sensors and to save some cost on the project. So the ability to determine initial condition of the state vector from the value of output, input, and the dynamics of the system is called observability. And then we determine observability using the rank calculation of an observability matrix. So we are calculating a physical property of the system using a mathematical calculation. Then we looked at examples of how to determine the observability. It is really simple, especially for the single output systems where you have only one sensor. And remember that your transfer function based systems are all single input, single output systems. So this is a system corresponding to some transfer function, some third order transfer function, which you can find by C into Si minus A inverse B, the formula that we discussed in the last lecture. And in this example we figured out that the system is observable. Then we discussed the Leuenberger observer, and Leuenberger observer is basically copy of the system dynamics plus a correction term. In the correction term, the gain of the observer, the calculation of the gain of the observer is basically what we call the design of the observer. So design of the observer, the logic behind the design of the observer is that we select the observer gain in such a way that the error dynamics are asymptotically stable, which means that error goes to 0, which means that x hat goes to x as time progresses. So we looked at a second order example. First of all we checked the observability, and then we designed the observer for the system. The size of the observer gain is same as the size of the transpose of the C matrix. And then we looked at the actual characteristic equation for error dynamics and then the desirable characteristic equation for error dynamics. Comparing the two equations, we get the gain of the observer, and then the resulting observer is something like this. Then we looked at another example. This was the third order example. We checked the observability, and then we computed the observer gain by comparing the actual characteristic equation of error dynamics and the desirable characteristic equation of error dynamics, and we get the observer gain. And then we looked at what the difference between the full state feedback control and the observer based dynamic compensator control. This control has the advantage of having lesser number of sensors which means lesser hardware, but that is at the cost of more software. So the programming of the controller becomes complicated compared to this one, but this complication saves you in terms of sensors or hardware cost. Then the example, we looked at an example of dynamic compensator. This is basically the same example for which we already designed the observer. We check the controllability of the same system, and we place the eigenvalues somewhere in the left half plane, and we calculated the gain that ensures the eigenvalue placement at our desirable location using the MATLAB command place. And then the observer dynamics of the resulting system are like this, and the controller the actual system dynamics are like this. So this was today's lecture. Hopefully it was understandable for you, and if not, let me know in the comments. Thank you very much for listening.